thanks for registering for the class. Otherwise they could, but I think it's the same link so they could just look up that old email. I'm trying to explain that to people.
Okay, okay, that would be great. Thank you very much, friend.
Of course. Get an email as soon as you register saying
Professor, I had a question about the project, but I
Yes.
can't wait to ask it if you want everyone to join first, because I think other people might have.
Yeah, let's wait a couple of minutes for others to join in.
All right, sounds good.
So far I have 42, and let me check my Zoom setting on the meeting.
Somebody says they deleted that email, one of the old emails saying thanks for registering, here's the link. And because this new one doesn't send a link, I guess they have no way to get in.
Oh, huh. And you cannot join in through the Canvas Zoom?
No, because I could screen share to show you what I'm talking about, but that just takes us to a registration page. And usually when we fill out the little thing with our name and email, it sends us an email with the link. But this time it says, I can read exactly what it says, but it says something like, oh, your registration request for this meeting has been submitted to the host for approval. You will receive an email regarding your registration status, but that email never comes.
Oh, okay. And it didn't send me that email either.
If you're able to join past sessions, that might work because all these sessions are this exact same. I've been using like the same link copy pasted since the very beginning.
Right. And yeah, I see now there are like 2 pending approval. I just approved them. So that's what changed. Like from this time, I thought like all of you guys are basically registered for all the sessions, right? So that's why I closed the registration, not closed really. I said that, okay, now I need to verify. Instead of automatically approve from anything from SJSU, I will verify myself and then approve that. That is the only change I made, but nothing else basically.
I think the only real issue is for the guy who deleted the old email, which has the link, which is specific to him, so he can't use anyone else's link.
Okay.
But I did send the YouTube link in the chat, so that guy should be able to at least look at the YouTube.
Okay, that would be great. Thank you very much. So I have like so far 50. Let me do one thing. Let me at least disable the waiting room for today and get everyone in. Yeah, maybe later, probably I'll request one of you, not today, but maybe sometime, just show you your student experience as joining this meeting, like and how we can improve that setup and all this stuff. That would be really great. So how many so far? 51. Yeah, I think people are coming in now. Maybe. Okay. Anyway, hopefully there would be no more glitches. Let me just quickly check if there are any other pending approval. So can someone please update in the Canvas discussion on the logistics section, logistic discussion, that the way you basically joined this meeting without re-registering. Because once you are registered, it will let you be in, right? That friend was asking, saying about the email that you got, you stored that email and use that same meeting ID and password to join in the session. You don't need to re-register yourself always. Okay, so yeah, let me like do time to time check these pending approval things or yeah. Okay, anyway, so this is the page, and what I want to do is CSU, instruction.com, model 3. Okay, let me share my screen with you. I see there are some interesting question in this module. I'm happy to see them. Do you see my screen, all of you?
Yep.
Okay, this is my Jamboard. This is the discussion. Okay, let's go with the first one. And also I'm opening the chat. Participate. Okay, all right. So the very first one, this is interesting question. NOR and NAND gates described in the lecture 6 include PMOS transistor and capacitors. I don't know the role in the circuit. The redundancy is the capacitor part of NOR gate. Okay, that's a good question. And then can we do that? So first thing, this specific NOR example, this is a NOR gate. Definitely this is a NOR gate. But this uses some technology called the bipolar junction transistor, BJTs. These device types are BJTs. And these device types are used to build digital circuit in old technologies, like maybe 70s, 80s technologies. Till there is a CMOS or BiCMOS technology appears. Let me try to explain that. What is this BJT doing and why the BiCMOS is better than BJTs, and that's then you will see why all the modern computing system actually uses the complementary MOS circuit like this. See, so you see the BJT the one you are drawing, or maybe simply let's draw a BJT inverter. Okay, let's not talk about NOR right now. Let's talk about the BJT inverters. That's your power source, and that's your ground. And this is a control, and your output is simply this. Okay. So in this circuit, what happens when you set this guy to 1, that means this guy is on, and As a result, current flows from VDD to ground, leaving this electrical state of the Y at 0. Now, when you basically make it to 0, then this path is cut off, and this guy become 1 simply because VDD now can supply current to the Y terminal. Similarly, on the CMOS side, or metal oxide semiconductor technology, we can have like an NMOS. This is an NMOS with a ground connected to VDD Y, and this one is a perfectly an inverter. Okay, functionality wise, this is a perfect inverter. How it works? Similarly, if you set it to 1, means this guy is on, and the current goes out to the drain and leaving the state of the Y as 0. No current can go into the Y direction. But as soon as you turn off these, means this is off, so VDD can actually supply current through the Y terminal, and that leaves the state as on. Now, question is, why shouldn't we actually use this one, BJTs, bipolar junction transistor? Versus MOS, metal oxide semiconductor. One reason is this: these devices are big, really huge, and these are very small footprint. So within a like 1 millimeter by 1 millimeter circuit area, you can pack more of CMOS devices than BJTs. Okay, that means you can actually have more and more complex function with the MOS technology than BJTs. That is one reason. There are many. That is one reason people move to the MOS technology from the BJTs. But BJTs are still in use, like very specialized circuit, analog to digital conversion, digital to analog conversion, and others like power circuit, power switches. Those circuits we still see BJTs are in use. It's not like it's not a dinosaur technology. It's still valid. But core of the processor are made out of the MOS. One thing is that because it's a small one. Now let's come to the next one about these PMOS, why if they're redundant or not. See that in this function, in these operations, we always have a current flow from the power source, right? Either it is going in the red direction directly towards the ground, or to the Y, the blue direction, but nonetheless, power is being drawn from the batteries, from the power sources, okay? Now, this stack up, which is called a BiCMOS technology, BiCMOS, or let's just call it a CMOS technology, which stands for complementary MOS. we try to eliminate the consumption of currents through this technique. Use a PMOS and an NMOS stacked up, draw the output, and this is my input A, this is ground, this is VDD, and now it works as a inverter gate, right? So how you can well imagine that if it is 1, if A equals 1, then this guy is on, this guy is off, right? That means nothing is going into the Y, right? Nothing is going into the Y. So that means it's a logical 0, okay? And if it is now, if I turn this to 0, which means this become off and this become on, then current actually start going into this direction. So you see, like we just eliminate the need for current drawing from at A equal to 1. So both this MOS and the BJT, this inversion circuit actually draws current even if A is equals 1, where output has to be 0. Some current is going and just flowing away into the ground without any usage. This CMOS technology, on the other hand, you see like when A is 1, then we are actually cutting off the VDD from the source. Nothing is basically like drawn from the VDD towards ground. Nothing is flowing, okay? But
hey, Professor, you don't need a capacitor for that?
Okay, now I'm coming to that one. That's a good question. Now, as friend asking like what the capacitor is, okay? So capacitor is not part of the inverter, okay? It's a model of the what this output is driving. This is called a load capacitance. What it does, it models so load in the sense electrical load. This inverter is driving. What does it mean? Remember, see that inverter is not used standalone in the computer circuit, right? It is probably driving another inverter. It is probably driving another NAND gate, or so and so forth. So look at this, each of this output. It is driving something else. So what this capacitor is representing is the driving load model of the gate under consideration. So instead of saying that, hey, it is driving this and that, it basically is saying that, hey, it is driving some load which has a capacitive nature, okay, which has a capacitive nature. So with that respect, now we can well explain this whole operation as, let's say I am at 0, okay? That means this guy, this NMOS is off and PMOS is on. That means it is actually charging up the capacitance. And that capacitance, charge up capacitance value actually driving the value, logic value of this output gate as 1. because it's a full load. Okay. Now let's say from 0 we switch to 1, the input. 0 to 1, we switch to that. That means now we have these guys off for the 1, right? Now we are considering this one. PMOS is off, NMOS is on. So that means nothing can charge back this capacitance, but there is a discharge path for the capacitance to get discharged and clean all these charges inside it, right? It becomes a 0 charge, and that gives your logic value 0 onto the Y terminal. So in a sense, this capacitance in this question is not a part of the inverter, but it is kind of showing you the operating model of the inverter. And then we can or in this case, it's a NOR, and how we can explain its operation. Is that clear? Any question, Alexander?
Yeah, makes perfect sense.
Okay. So for this class, let's not go into the BJT technology. Let's stick to the CMOS. That's what we use in the modern computer. Okay, next one. How the NOR is holding. Okay, let's look at the NOR, right? Once more. So the NOR. So what we are trying to do here, this one, right? Started with a logic 1, and we are feeding back the output. Let's try to explain its operation. So let's first draw the pull-up part. So this stack of the PMOS is called a pull-up circuit. This is called a pull-up circuit. And then,
oh, Professor, we can't see the Jamboard.
oh,
now.
sorry.
Thank you.
Okay, this stack is called pull-up circuit. This is because, you know, like as I was explaining in this previous one, this basically when we need to make a logic to 1, this path is on, and it pulls up the logic from 0 to 1. That's why this upper stack is called the pull-up circuit, and the lower stack, NMOS stack, is called pull-down circuit because it's turned down the logic from 1 to 0 by discharging the load capacitance in the model. So we write it down. This is pull-up, and then we draw the pull-down circuit. Okay, and this is my output. This is what the load is. Load capacitance. And this is VDD, ground, etc. Now, let's try to get it. Okay, first we applying, let's say this is A, this is B. That means my B is connected here, right? That's what the feedback, we are feeding back onto the B, and A is 1, let's say. A is 1, okay? Okay, A is 1. So 1 means this is on and this is off. And this is on means what? This on means I have a discharge path for discharging this current to the ground, right? And this is off. The other PMOS is off means there is no current flowing through the VDD. It's basically shut it off. That means this guy will go to logic 0, right? And then let's say you make it to the high Z, like you disconnect this guy. You make it high Z, and this is 0, means B is fed with 0, means B is, wait a minute, B is on, right, in this case? B is on, and but this one is on high Z, means it is electrically disconnected already on the high Z side, right? It is high Z, this is high Z, which one? Yeah, this one is high Z. So these are all electrically disconnected from the circuit. So that means there is no path actually going to charge this capacitance. And even if this PMOS is on, okay? And of course, since this is 0, this is off. So doesn't matter whether off or on, we still have a 0 charge on this capacitive load, and we retain the 0 value on the output, even if we basically cut off the input signal, make it a high Z. Question?
Shouldn't there be a connection, the B back to itself connection? Shouldn't there be like a line connecting the line next to Y back to B?
Yeah.
But on the, I wish I could point. No. Yeah, but that's a.
That's a
Oh,
Y.
right. That comes that way and goes back to B. Sorry, dumb. Thanks.
That's the one. Yeah, transistor level, it's get little bit confusing and complicated because of so many elements are there. So, but anyway, this class will stick mostly onto the gate level side. We will not go much into the transistor level circuit. Question?
So just to confirm, if the PMOS has an input of logic 1 or it's in high Z state, then no current passes through the gate. And only when the input is logic 0, then it allows current through?
Right.
Okay.
Anything if you are basically take out the gate control, this high Z control, then it basically you can treat that element as an electrically disconnected state from the circuit, the entire device.
And the same thing holds for an NMOS gate?
Yes.
Okay.
Okay. I have one request from Anjali. Yes, I will go with one example today. Let me see if I address the other questions similar. So friend, I think I answered your question, right? Yes, this is a, but
not the second half. Or no, sorry, that first question, but the why do you need the, as you were talking, I was thinking about it, and I'm thinking it's because we want the state of 0 to really have some sort of power output.
right.
And that's why we want, but I am still not 100%. I'm like, why won't the charge disappear on its own? Why do we need the capacitor to send it to ground?
So, okay. So this is an inverter, right? That's what you are proposing. Yeah, this is a simple inverter like we did here, right?
Yeah. So why would we even want the other form with a capacitor and a second and an NMOS underneath, like you did there
Okay,
on the
so
right?
yeah, so this is for power saving purpose. This is for to save power. Like low power
Oh,
designs, all the low power designs, right? In the earlier this MOS configuration in your example, right? If the output is zero, like with by setting this guy to one, even in that condition, you have current is flowing in the circuit. So something is drawing current from your battery to the ground. Your battery is being discharged continuously. But in the CMOS technique, complementary MOS, we place the MOSFET, PMOS, to stop that current to going. And we added the C load just to explain the functionality of how this circuit would work. This circuit alone is not kind of sufficient to explain what is going on. So that's why we introduced this load circuit to explain the whole thing. So, but this is not a part of your inverter or any gate circuit anyway. It is just to
got it.
explain how the things work.
Okay. So with the CMOS stack, but without the capacitor, it still would work as an inverter, just like on
Yeah,
its own. But it's more like it. Yeah. Okay. Got it. Thank you.
yeah. So this is more like to explain the functionality, how it works, like what happens. Basically, your load circuitry is charged up, it's stored, and it's kind of it cannot be discharged because the other transistor is off. So it stays at logic 1. And then as soon as you turn on the NMOS, turn off the PMOS, all this charge is kind of discharged and make it like 0. You don't stay at 1 at that point. So to explain that phenomena, we basically add this C load and to explain the whole operation. Okay, and yeah, so this was, I think we were discussing this in our office hour, friend and me. So he has this question like all these complex function, for example, this one, right? X greater than 12, etc. Are they all kind of pre-built into the ALU and only we select what we need? The answer is only the fundamental functionalities are pre-built in the ALU, like an addition, subtraction, division, multiplication. We'll go through this ALU design in the class in I think successive 3-4 lecture down the line, and we'll design an ALU at the gate level. But then we'll see that we have only the fundamental operation. The complex operation are broken down into fundamental ALU operation by the compilers. Okay, so for example, like ALU may support a less than operation natively, but it does not support a greater than operation natively. So what compiler will do with this statement, high level statement, it will basically break it down into not of x less than 12 or and x equal 12. Equality is a fundamental operation maybe in the ALU. So in that sense, it basically breaks down into whatever functionality that target hardware ALU has, and compiler understand that target hardware and generate the more fundamental operations for the processor. That's how the computing system works. Okay, questions so far? All right, then we basically, let's take an example. Okay, let's take an example. Okay, we'll need to design and implement a digital circuit detects a 4-bit number XYZ, and which is basically if the incoming number incoming value represented by WXYZ is less than 3 or greater than 12, or it is divisible by 3, then it output is 1, which is out is 1, otherwise 0. And we need to implement it with a NAND only logic. And we can assume there are multiple NAND input gate available, 2 or more inputs, and etc., etc. And we'll do that. And also we'll assume this incoming 4-bit number as an unsigned number. Let's not even think and make our life complex with the signed number. All right. So these are unsigned number, and that's what the circuit we want to build. With that preview, let's take 5-minute break, like 8:15ish. We'll be back. Not 15, 3 minutes, 10, yeah, 12, 15, about that. 5-minute break. All right.
Professor, you're muted if you're trying to talk to us.
I was mute. Basically, what I was saying that I got some message in the YouTube live stream chat, and what I suggest you guys to find out the old email that you got from the Zoom with the meeting link and the password. That should work for you. Maybe you want to re-register. I don't know. Like, and there is, I think, friend has updated discussion page on how to join in this session. So maybe that can help you.
Oh, sorry, I didn't do that. I was just telling people in the Discord, but I'll put that in the discussion page right now if you want.
Oh, okay, that would be great. Thank you very much, friend.
Of course.
I was locked out for a while, and I had luck by re-downloading the calendar. I got back in.
Okay. So if you are listening to the stream live, can you please follow those suggestions and see if you can get back into the class? Okay, let's see. Now we are trying to design this circuit, and so with this description, right, what we need to do is first to draw a truth table, right? We have to have this function implemented. Function wxyz equal to something, like some Boolean function. So we first construct the truth table of this function out of it. Wxyz and the function. And then we note down different values of this input combination. 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. And I think let's continue. Wxyz.
Professor, you're on the wrong page on your screen.
Oh, where am I?
Page 18.
Oh, yeah. Thank you very much. Thank you. Sorry for that. Okay, so let's continue this truth table. 1 0 0 0 1 0 0 1 1 0 1 0 1 0 1 1 1 1 0 0 1 1 0 1 1 1 1 0 1 1 1 1. Okay. So now see the what is the unsigned value it represents? This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now your description of the problem says that output goes to 1 if this represented number or value is less than 3 or greater than 12 or divisible by 3. That means less than 3, 0 is less than 3, 1 is less than 3, 2 is less than 3, 3 is divisible by 3. So for 4, it will be 0. 5 doesn't fall there. 6 divisible by 3. So output 1. 7 is 0. 8 is 0. 9 divisible by 3. 10 is 0. 11 is 0. 12 is divisible by 3. 13 greater than 1. 14 greater than 1. And 15 greater than 1. Right? Now, for that, we note down the mean terms. We know that mean terms are like M1, M2, M3, etc. Like these are all mean terms. M6, M7, M8, M9, M10, M11, M12, M13, M14, and M15. So that means we can write down the function as sigma of M 0, 1, 2, 3, 6, 9, 12, 13, 14, 15. Right? So far, so good. Any question? Okay. So my function was what? Wxyz is sigma of M 0, 1, 2, 3, 6, 9, 12, 13, 14, 15. Now we draw the K-map to optimize this circuit. Zero, 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 one, 1, 1, 1, 0, 0, 0, 1, 1, 1, 1, 0. Let's mark the cells. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then put 1 into those cells. 0, 1, 2, 3, 6, 9, 12, 13, 14, 15. Right? Did I miss anything? No. Okay. All right. Okay. So let's see. Now start grouping. Okay. Now start grouping. So definitely this is one big group chunk. This one is a chunk. And then for this one, I have two options. One is like 2, 6. Another way would be like 6, 14. Right? And I have okay, now I have two options for the 9. This one, right? One is definitely this one. And another would be maybe this one, right? So far, okay? Question? All right. Now, let's look at the primary implicants, okay? PIs. What are they? They are definitely for this one, 0, 1, 2, 3, and this one 12, 13, 14, 15. And then we have sigma 2, 6. And we have sigma 6, 14. And we have sigma 9, 13. And we have sigma of 1, 9. These are PIs. Now essential prime implicant. Definitely this one and this one. We cannot avoid that. 2, 3, 12, 13, 14, 15. Now I have choice between this and this. I can pick up any. Okay, nothing has advantage over another. So let's pick up randomly like this. 2, 6. And maybe let's pick up 39. Okay, so these are by choice we are promoting them to the essential API to make the function. So now the function, before I go there, any question on the so far? Okay, now let's write down the reduced equation. M0, 1, 2, 3. It will be W bar X bar. Then the next one, 12, 13, 14, 15. It is WX. Or 26. Sorry, 26. That one we picked up. 26 is basically within this group. We see W is at constant 0, so W bar, and within these both Y, Z are constant. Y as constant at 1, and Z as constant at 0. So Z bar, W bar, Z bar. Okay, W bar, Y, Z bar. Okay, and okay, and the next one is 13, 9. That's what we choose, right? 39. So for that, we see that W is constant at 1 and Y constant at 0, Z constant at 1. So this becomes my reduced function. Now our problem is not done at this point. We'll further need to reduce it using the NAND only operation, right? But so far, you have any question? All right.
Oh, hey, Professor, I actually, like for an exam situation, in which, well, not just an exam situation, you would always want the one that results in the least amount of operations. And when it's like this, where it's kind of symmetrical in the amount of overlap, I'm assuming it would end in the same amount of operations. But are there any cases where it couldn't? Like, do we always need to check each combination?
Unless it is very much specified that come up with the least number of gates, then no.
Cool, thank you.
All right, so now we basically operate on these functions Wxyz equals W bar X bar or Wx or W bar YZ bar or WY bar Z, which is, I'm just copying that, okay, which is now apply De Morgan on top of this. This become W bar X bar whole bar, WX whole bar, W bar Y Z bar whole bar, and WY bar Z whole bar, right? We just apply De Morgan. Assuming these are single terms, so what I did is basically, if you think this is simply something like A or B or C or D, what I did is A bar, B bar, C bar, D bar whole bar with the De Morgan. Okay, so let me just use that. Now we have, and we all know how this W bar, like this individual inversion we can make. Okay, so it seems like we need to have inversion for all the variables. WX is inverted, Y is inverted, Z is inverted. So we need inversion for all of them. And we know this is nothing but this is W bar, this is X bar, Y bar, Z bar, and now we are combining them with the NAND. So W bar X bar, that would be one NAND. And then WX, which is like coming from here, X is coming from there. This is WX whole bar. And then we have W bar YZ bar whole bar. W bar YZ bar. Okay, W bar Y Z bar. Whole bar, and then we have WY bar Z bar. W here. WY bar Z. Z is right here. Another NAND, which is WY bar Z whole bar, and you NAND them.
And are you doing it this way, where you've demorganized it, so you don't have to use non and slash or ones? Like you can use all the NAND slash NOR ones, which have one less operation, because you don't have to invert them into normal and slash or.
The reason that we are doing it, because let's say when we are actually implementing the digital circuit, let's say we don't have any OR gate or inversion gate we now have. What we all have is a NAND gate.
Got it.
Then how do we go? It is nothing to do with kind of optimization. Sometimes it does, but not in this case.
Oh, it said it in the problem. I totally missed that. Thank you. Got it.
Yeah. So it's sometimes like some logic libraries may not have some certain, like logic functionality available. So the problem is that how to replace them with the existing functionality. So in this problem, it says, hey, you have only NAND gate. to express the whole thing using a NAND gate. Okay, so with this thing, what we can do now is actually have this one implemented in the Verilog, right? So let's try to, we have like about maybe 10 minutes. Let's see if I can quickly do that for you. Let me bring up my model sim. Some projects. Okay, so do you see my model sim screen, model sim window?
Yep.
Okay, I actually have two variation of it, just to give you some demo. One is the behavioral level description. Okay, what it says that, okay, I'm taking an 4 input, WXYZ, and an output. And inside that, I define this like this, like a real number of which called QR, an integer unsigned is numQI. I'll explain what it does. But main body of this behavioral model is that always at the rate WXYZ means if any one of this bit value changes, execute this. Okay, with the initial value out to 0. One point to note that, see, in the initial block, since it is a single statement, I didn't need to do and begin it. It is just one single statement. If it was multiple statement, then I had to enclose it within the begin and end block, right? Begin and end block. Anyway, so what we do as soon as some input is changing, basically we assign that bit pattern, 4-bit pattern, into the num. Num is an integer unsigned. Okay, it is 32-bit there, but that doesn't matter. It just assign that bit values into a value, change it to, and then I check that integer value, if it is less than a 4-bit decimal 3, or like I could have done these things also 4-bit decimal 12, but anyway, I'm just showing you different variation you can write. Num greater than 12, then make the out as 1. So that is two condition fulfilled. Else, now we need to see if it is divisible by 3. So how am I doing this one? This one, I am basically using the QR, which is a real number, real quantity. I am dividing that with 3, the num, and also the integer QI, I am dividing with 3. That means this part, line number 17, is a real division, like real number floating point division, and line number 18 is an integer division. Then I am checking if the QR and QI, that quotient from the real division and quotient from the integer division, are the same value. If the num is divisible by 3, then they ought to be of same value. And that's what I'm checking. That's what I'm setting this value to 1 if it is divisible, otherwise divisible by 0. That is the behavior description. Okay, that is the behavioral description. And on the gate level description, what I did, actually I derived a little bit different logic than what I just showed you. It is basically I picked up the other combination of the primary implicant. But nonetheless, what is happening, I basically, if you look at the Jamboard here, like look at this circuit, right? So taking WXYZ at input, output as out, and I'm defining words like W bar, X bar, Y bar, Z bar. That's what the NAND line number 9 to 12 is defining all this W bar, X bar, Y bar, Z bar that way. And then from 14 to 17, I'm combining them into these other terms, W bar, X bar, whole bar, those terms, I'm combining them. And then finally at line number 19, I'm combining into a big NAND with the 4 input with the output as an out. So it will give me the indication of that. Then as a test bench, what I did, I basically want to drive this model, and the corresponding behavioral model with these different input patterns, right? And that means I need to drive it through some register. That's what I'm defined a 4-bit register in, and I'm observing the output from the behavioral model as an out underscore B and from the get level model as out underscore G. And I have some like bookkeeping integers for the number of tests, number of pass, etc. Then line number 9 and 10, I instantiated the behavioral model and the get model. And then from 12 to 32, this is basically the test bench operation. What I'm doing on the line 15, I am practically going with the loop, setting values from 1 to 15, 0. So initially with the 0 and then changing to the 1. Then what I'm doing, I am basically driving the in register array with the 3-bit, with the 4-bit of that integer value of I. So in will be fed with this bit pattern for 0 to 15. And then I'm testing the equality out of the output from these two models, behavior and get level model, equality. And if they are equivalent, then number of pass is bumping up and printing some status. So in this way, what I can do, let me see how much time I left. 3 minutes, that's enough. But I want to introduce you to some very interesting feature in the models through this. To do simulate. No, library work. Let's load the test bench. And in the instance, in fact, the whole thing, actually, you can do something like add to the data flow. Okay, add to the data flow. So what it does is basically gives you some visual debugging feature that you can use in your debugging method. Okay, that way, let me just, where is the zoom? Okay, I'll come back to this one. And then let's feed these 3 into the wave. Okay. Now we simulate. Done with the simulation, feed the whole simulation in the window. And we see we are feeding up different values here. Let me just change the radix to unsigned. So see, we are feeding 0, 1, 2, 3, 4, etc. till 15. And we can check that, okay, result is consistent, like less than 3, equal to 3, it is 1. Greater than 3, it is 0 unless it is divisible by 3. It is turning 1. And both behavior and get model are working fine. That's okay. Now let's look at here in this data flow diagram. Let's just undock it. Undock, then fit. Now we can actually look at unfold the selected, or maybe let's look at here. So this is what it is doing, the initial block that is driving the different values, like in is a value, right? And I can actually expand it to the drivers. Or layers. Okay. All right, so now let's fit in. So you see, like, it basically shows you this in is feeding into which part of the circuit. It's practically drawing up your gate under the interest. And at the same time, you can operate on the waveform. Let's undock this. And let's bring them out together. I want this, I want that. Yeah. You can fit this. Okay. Now let's say I want to observe here. See, your data points are actually changed at this whole circuit, and you can actually follow through what are the different values being fed in and what are the logic output being generated and how it created that logic 0 out of that. Similarly, if you go here, let's check this guy. See, the logic value gets changed, and you can follow through your circuit in this way, in a visual way, to debug things through your implementation. And this is useful in case you are actually dealing with smaller circuits. And if it is hierarchical, it will probably, it won't expand everything, but it will go into the specific components, and you can follow through how the logic value travels through your logic of networks. This one is very much useful for your gate level modeling, I would say. This part, this is like an behavior model, right? So it cannot show anything like a logic gate level. All it knows, I have a behavior model of this guy. Like if you double click, it basically will show you where the visual model is. I think here it's pointing out, okay, this is my block, always block, and it is basically picking up input values at WX, YZ and putting out some value out. And you can actually follow through different combination of logic and what it is spitting out. But debugging is more like at the code level. But at the gate level modeling, you can really visualize that and follow through your logic and how that evaluation goes on and see where it actually gets a wrong answer. And you can also expand this, like where, like you can select it, expand to the driver. Yeah, so expand it to the NAND 6. So I think we have all the gates here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So this is the entire circuit that you have the logics, connected logic you can debug and trace. Question?
We had a question on the project that is super quick.
Sure.
If there's nothing to talk about here. We were just wondering about negative values because you don't specify exactly. And somebody said that they asked you in office hours and you said we couldn't just use the less than operator for SLT. We needed to.
Yes, less than operator won't work for every scenario.
But it would if as long as we specifically cast them to signed.
Oh, so you can
the operations. So would you be okay with that, or do we need to do it? Do we need to do it the way?
As your behavior model is okay and give right result for all the combination, that should be also okay.
Cool, thank you.
Yeah, from my point of view, like I was more trying to drive you into thinking how the ALU does work. So
right.
ALU, how it does, it basically subtract these two quantity and look at the sign bit of the result. And if it is a negative, then it is a less than. If it is not a negative, then it is 0, basically false. So that's how logic level works basically.
Makes sense. But I think, wouldn't we still need to in Verilog, because it treats everything as unsigned, wouldn't we need to wouldn't we need to cast just in case? Or if we're using a negative number in our test, wouldn't we need to cast it anyway if we did the subtract and get the most significant bit way?
In the behavior model, you can still do it, But if you think from the hardware perspective, like a ALU does not actually know about signed or unsigned. It just operates on the bit patterns.
Oh yeah, totally. No, I'm just saying, like, so if we do it the more ALU way, like you're wanting us to, and I totally get why. Don't I'm just asking to better understand Verilog. Don't we still need to cast because it would just treat them as unsigned and try subtracting if we gave it 4 and -7.
There is a cast operation in the Verilog. You guys need to check it. But definitely what you can do, you can assign that registered bit pattern to an integer variable, just we did in this example, right? And then operate on that. That is also possible.
Okay.
Right. So here, if you see, I hope I'm still sharing behavior, right? So here you see there is the integer number, and I am actually assigning that value with some bits. You can assign some register onto some integer value and then describe your behavior on top of that. That's also possible.
Okay. Cool. Thank you.
Okay. All right.
Sir, is it so when I run a test for a subtraction and it's like it should output a negative number, so let's say 2 minus 3, instead of outputting -1, I think it outputs integer max. However, when I do it the other way, it also outputs integer max and like it says test is passed, even though it doesn't like show -1.
Yeah, that is because the $right, that Verilog command actually treats everything as an unsigned bit pattern. So that's why it is normal. It is okay.
Okay. And then I also mentioned that I wanted to ask a quick question that might be helpful for everyone. You said in your instructions for the project only to upload ALU.v, project1, testbench.v, and project definition.v. So does that mean we leave out all the other files that are created when we do the project, like the BAC and the...
Yeah, you don't need to upload them, right? It's in fact, like I basically we pick up your ALU.v and test on that with our own tester.
Okay, perfect. Thank you.
Is there any other question?
So would it be possible to resubmit the project if we already did and we didn't know it had to include negatives?
Sure, as long as you are within the timeline, yeah. Yeah, we always evaluate the latest submission unless otherwise you requested us. Does that answer your question?
Yep, thank you.
Okay. Oh, by the way, Anjali, is the now are you clear on the how the design steps work?
Yeah, it makes a lot more sense now.
Okay, great. Good to know that. All right, then I'm stopping recording and also streaming. Good night, everybody, and see you on Wednesday.